So the first thing we're going to do today is go over spot check some answers on the homework so you can check your work. So part A, you should get a lift curve slope for the airfoil. That's it. About 0.1 per degree. Is that what you're getting? All right, and then make sure you converted it per radian before you use it in the big formula. And then when we're doing the big formula, wing area, 400 feet squared, aspect ratio, 4.41, little k, 0.91196. We're using a Mach number of 0, so beta is just 1. C over 2, sweep. Tangent should be that. Everybody matching? Looking good? And then big K, I got 1.068. Yes? Thumbs up? Okay. So then you should get I got 4.06 per radian for the finite wing. And again, this should always be less than this. This is like 6 or 5.73. And then for the plot, just plot CL versus alpha for the range of angles of attack. So all you're going to do is go into Microsoft Excel or plot by hand or something, whatever you choose to do. So give me a plot. It's just to show that that's what the lift curve looks like. And here we're assuming that there is no lift at 0 alpha. I mean, that could change, but we're just going to plot this for now. So any questions on those? That's the first 3 problems, really. What do we got in the chat? So I think it's possible if you're on Zoom that if you talk, I can hear you through the computer here. Somebody say something.
Testing.
Yep, I hear you, David.
Awesome.
What was the question that came up on chat? Double the surface area. That's just the total area of that wing should be 400, right? Yeah, I've only shown you half the wing in the picture, so there's another half of the wing sticking out the other way. You guys figured that out, right? Yeah. All right, let's spot check the integration formulas. So when you're doing the area, after you do integration, you should get with those limits, and then you plug in the limits, you do the algebra, and you get there. So that's a spot check on that. And then on your C-bar, set it up, do the integration. that big enough it shows up on the screen? Looks pretty good up there, doesn't it? Okay. Of course, there's a bunch of algebra after this. At some point, you're going to have to factor out a CR squared. So this takes about half a page to do that. And then we give you a spot check halfway through the Y aerodynamic chord. Oh, by the way, along the way, you're going to have to substitute in the formula that we got for the area. Right, we have 1 over S, so make sure you substitute that in, because that gets rid of the S, and that's where this thing showed up anyway. Everybody good with that? Again, there's a lot more you need to show. Yeah. You have to shout. I'm sorry, it's just hard to hear with the mask. Where'd the other two come from? Yeah, the B over 2. Yeah, it's and then the 2 flipped up, right? Yeah. Okay. No, please ask if you see something you don't understand. The point of this is that you go, well, wait a minute, why is that? Yeah. No, you need to substitute because the final formula doesn't have S in it. So you're going to have to substitute the CR plus CT over 2. Yeah. And let's see, Y MAC, spot check on that. You should have gotten this after the integration. And then again, you'll have to substitute in for S. And then along the way, you're going to have to factor out a B. And remember, lambda is the ratio of the tip chord to the root chord. So you'll have to rearrange things to get that in there. So let's see, I guess somewhere before here, you have to factor out the root chord. You'll get an expression, you'll factor it out, and that's what gives you the ratios of the CTs over CRs. Well, I'm going to show you a shortcut for XMAC. Takes the whole page if you just brute force it. So if you look at this thing here, and just the Y, so you leave out this stuff, and this, that is the formula for YMAC. So that's a hint for the shortcut. You've already done YMCA, no, YMAC. So you can quickly get this without going through the whole page. And then answers for the last problem. We already did the area. C bar should be 9.88. Y. That's an F feet. Sigma is 0.5. You guys getting these answers when you did that? Again, make sure that you are working these problems before today, not procrastinating and trying to do it tomorrow night. And occasionally I'll do a spot check to make sure that you are attempting them before the day that we go over them. Okay, any questions? I think you got enough to check what you're doing and make sure you get it right. Yeah. Oh, that's fine. Yeah, I mean, if you got 2.9, that's obviously off. So I guess, yeah, carry 3 decimal places on most stuff. I mean, the rule of thumb is the data going in, you carry the same precision right along the way. But typically 3 decimal places will get you 3 significant figures. Okay. And again, a reminder, since I do go over the answers to these, what is graded is not that you got the right answers, but that you show your work. So make sure you show your calculations. When you're doing like this, show the formula, show the numbers that you plug in there to get the answer. Because homework in classes is just like practicing in any other thing. Like if you play basketball, it's practicing what you do as an engineer. Okay, with an airfoil, we've talked about the force and moment model of the distributed load. There's pressure forces all around the airfoil. And we want to resolve them into a force and a moment, just like any other distributed load. And we found out the best place to do that is about the aerodynamic center. Because as the angle of attack changes, the additional force, the additional lift acts at that point, and so the moment doesn't change if we take moments about that point. So we'll typically call that the moment about the aerodynamic center, or CMAC. So that's our force and moment model for the airfoil. But now we're going to put airfoils into a wing. And so once we get this force and moment resolved onto the airfoils, now we're going to have a distributed load along the wing span as the airfoils are put into the wing. So we have to do the same thing. We have to take the distributed load there and figure out the total force and the total moment of the wing. This is the kind of thing that is typically done by what's called the loads group. For flight dynamics, we need to know the lift and the pitching moment because those are forces that are going to drive the dynamics. But more importantly, perhaps, the structures people need to know how the lift and the pitching moment are distributed over the wing so that they can design the structure to handle that load. So there's a loads group that figures this out for the wing design, where the forces act on the wing, how much they are. There's a huge load at the wingtip. They've got to design the wing box to handle that. We're interested in what forces are applied so that we can calculate the dynamics. We'll use Newton's law. Some of the forces is matched times acceleration. So I'm going to draw you a picture. We're not going to go through all the details of the formulas for this because it's totally dependent upon how the wing looks and how the wing is twisted as well. So it's very specific to how the wing is constructed. But we need to understand what's going on. So draw our half of the wing again, like this. And so we're going to talk through this with pictures. So there's the wing, and it has cross sections that are airfoils. So I'll draw some of those in here. And in complete generality, we could have a different airfoil at each spot along the wing, each spanwise location. Typically, that's not always optimal. But also, we could take the airfoil at the tip and twist it down or up. And a lot of times that's done so that the tip does not stall before the root of the wing. If you get the tip stalling, then you get huge rolling moments when stall happens, and that's bad. So typically you'll twist the tip a little bit downward so that this airfoil stalls before the tip. So like I said, the structure of the wing, how it's put together, complicates this calculation, but at each airfoil you have its own aerodynamic center. And notice I've swept the wing, so that means that the aerodynamic center of the airfoil is not lined up straight across. There's a line of aerodynamic centers going through like that. And so each airfoil has a force acting at that aerodynamic center. And there's a pure couple. So what we want to do is resolve that distributed load into a force for the whole wing and a pure couple for the wing. And the point at which that acts is the aerodynamic center for the wing. Because just like for the airfoils, there's a point where the additional lift acts as you increase the angle of attack. And if you take moments about that point, the force increases and decreases with angle of attack, but the moment, the total moment does not change with angle of attack. And that's nice. We can say, okay, the moment is this much, and then the force depends upon the angle of attack. So the moment of the wing acting or taken about the aerodynamic center of the wing is constant. I'm off the screen here. Now, finding this point is, again, dependent totally upon the wing, how it's all put together. But that point is called, the X location of that is X bar, and the Y location is called Y bar, the wing aerodynamic center. And it might be easy to confuse these terms that we've already talked about with those, because you see AC, and you might think aerodynamic center. But remember what this is the location of the mean aerodynamic chord. So these are the locations of C bar, that mean chord. That's just locating that average chord in here somewhere, which is not the same as the aerodynamic center. So make yourself a big note that the AC in these names does not mean aerodynamic center. The bar notation gives us where that force and moment acts on the wing. Now I want to show you formulas in general for this. I want to leave that up because I want to come back to it. So I created my own presets for our camera. So let me get that to work. You're seeing the other board now, right? And I'll pop back over there for the people on Zoom here in a minute. But if you want to calculate the location of the aerodynamic center for any general wing shape, there's how you have to do it. Just like the formulas for the area and C-bar and all that, if you have some weird wing shape that's not straight tapered, you have to use an integration like this. So this would be if you had that wiggly wing that I said, well, you know, if you really wanted to, you can make your wing look like that. Looks really cool. Everybody be impressed, but it's really hard to build. It's really hard to calculate. And there's similar formulas for the Y and Z locations. And this one's the same, except there's a Z here instead of the Y. And I'm showing you these because when you start grumbling about having to use the table in the back of the book that I'm going to show you next to calculate those, think about having to do these integrations. So there's tables and formulas for standard types of wings. So that's what I'll show you next. Everybody caught up? You copied those down? Yeah. Did I get that backwards? Let me look at my... Which way? Yeah, it is, because typically in the body fixed axis, X is this way. And we're integrating Y. I did this backwards. I apologize. Thanks for noting that. Let's see, let's switch over here. So everybody's got those formulas, right? So the mistake I made here, I put X, this should be Y. And it's only for calculating these wing planform parameters that we do that. When we go on the airplane in the dynamic axis, we have X out the front, Y out the right, and Z down. And that's what, that gets a little confusing. So just remember this axis is only for calculating the wing stuff. And once you get the wing done, then we go on the airplane, we're in the airplane axis system. Yeah, because we're right-hand coordinates. X curl into Y, so Z's out this way. All right, so once you have this thing all resolved, then we don't have to draw all this stuff anymore. We simply draw C bar through the aerodynamic center and show the forces and moments on that. So a side view of our airplane now is going to look like this. So this is the mean chord. You just draw that. You say that's our average chord. Here's the aerodynamic center. And we draw the aerodynamic force, which we resolve into lift and drag. And then we say there's a pitching moment here. So this is the net resultant of all of that distributed load. We're saying it acts at the aerodynamic center. And there's the net couple for all the whole thing. And this thing is not easy to calculate, because if you look at this picture, you get all the pure couples from each of the airfoils. You have to add all those up. Plus, we're taking moments about this point, the aerodynamic center, so like this force creates a moment that way. This force is below it, so it creates a moment that way. So you've got to add all those up. So there's two parts. And there's integrals that I'm not even going to show you that need to be calculated, and that's all done by the loads group. They've got to keep track of where the forces act, where the aerodynamic center is, and calculate that. So you're going to use, where's my sheet? You're going to use a table back in the appendix in the back of your book. I just erased my formula. Did everybody get that down, or do I need to draw it again? Did I do that too fast? Somebody raise their hand. Anybody not get it? Everybody got it? How about on Zoom? Again, please. It's because of the lag on the internet. Here's C bar. Here's the aerodynamic center. Force. Lift. Drag. Pitching moment. So that's our free body diagram of the wing. I'll write down here so I don't do that again. So what you want to look at to get Y bar is table C.1 on page 359. There is a table where you look up Y bar for different lift distributions. And the lift distributions have to do with how the lift is distributed over the span of the aircraft. So I will tell you, when you do a homework problem or on a quiz or an exam, I'll say, choose this lift distribution. So you look up that line in the table, and you pick out the formula for Y bar. And then you need equation C.1, comma 5 that gives you X bar. I need to write this over here because I'm going to run off here. So you have to look up Y bar in this table, then you have to stick it down here. And then you need, I need to tell you what N is, and I need to tell you what this angle is. So if you're flying subsonic, N is 1/4. And so the angle that you need is the quarter chord sweep angle. So that's the angle of your wing 1/4 of the way down. And I gave you a formula for that. And then if you're sonic, then N is 1/2. That means that the aerodynamic center is about halfway down the chord. And for those of you that I showed the video in 324 faster than sound, they talked about that was a big deal in aircraft as they got close to the speed of sound. The center of lift on the wings shifted back, which caused the airplane to pitch more nose down, and they dove and kept diving into the ground. They couldn't pull out because that shift caused it to nose more down. So that was a big deal that they had to discover. Which one? Oh, I just totally messed that up. That is the half chord line because N is 1/2. So you plug in N and then it's N is 1/2, so C over 2. All right, so that gives us the ability to make this free body diagram for the wing. So the next thing we're going to look at is let's put a wing with that free body diagram on our airplane and see what happens. How are we doing on time? We still got time. Now, the next thing we want to talk about is pitch trim. Everybody good with this? So I can erase it. So two key features that if your airplane doesn't have, you're going to crash immediately. Is pitch trim means that the total moment of your aircraft is 0 because the moment of inertia times, let's say, alpha dot, sorry, the angular acceleration is equal to the sum of the moments, right? So if your total sum of the moments is not 0, then you're going to get pitch. So the airplane's going to pitch up or it's going to pitch down. So the first thing is pitch trim. This is equilibrium for the aircraft. Just like when we talked about the marble in the bowl, we said, well, there was an equilibrium spot with the marble at the bottom because all of the forces were balanced and it stayed there. So in our airplane, when it's flying, we want the total net moment to be 0 for pitch trim. And then static pitch stability is that if there's a disturbance from equilibrium, then we want a force, or in this case, a moment, to be generated back toward equilibrium. Doesn't say that it goes back to equilibrium. That's the dynamic part of it. All this says is that if we have a disturbance, like our ball, that there is a force in that case, or with the airplane, a moment that gets generated that wants to push it back to that equilibrium. So let's talk about just pitch stability and draw a picture here. And what direction do we want this to happen in our airplane? So let's draw a picture of this is a force, a free body diagram. Of a conventional airplane. The normal airplane. So here's our airplane, cockpit, vertical tail. Here's our wing. Here's our horizontal tail. So on the wing, we have lift and a pure couple. On our tail, we have lift and a pure couple. And let's say the CG, the center of gravity, is like right here. Can we get pitch trim? We got, let's say, a nose up moment there. By the way, which way is positive pitching moment? Now we have to go back to page 16, right, or 19, where I told you to put the paper clip. X-axis is out the nose. Y-axis is into the board, so I put an X there. So thumb along the Y-axis, fingers curled this way, so this is positive pitch. So we're going to get a pitching moment here, a pitching moment here. Lift of the wing, let's put a W on that, is going to be a positive pitching moment. But the tail can, because it's behind the center of gravity, will actually be nose down. So nose up, plus nose up here, and nose down. So it sounds like if we can adjust things, maybe make this distance really small, that we get a small moment from here, and then we've got this big moment arm so we can have enough to the tail to get pitch trim. Looks like we can do it. So pitch trim, check. It's a balancing act. We want to make sure that we adjust the location of the CG so that we don't have to have a whole lot of lift on the tail. So pitch trim. How about stability? We're talking about now the angle of attack changes. Maybe a gust or the airplane pitches up for some reason. So we know that the pitching moments stay the same with angle of attack. And we'll write this out in equations. We're just talking through it. But these lifts are going to change. Does that show up on the overhead okay? More or less. Let's try green. I want to make that difference because that's the delta lift due to the disturbance. I don't know if that's going to be any better. I guess it's okay. So we get an increase in both of those. Is there a force, and in this case, a moment generated to return it back to equilibrium? So the nose pitches up for whatever reason. Is it going to return back to equilibrium? And the correct answer is we don't know. Because it's going to depend upon where the center of gravity is and where the net resultant of these two forces acts. So we have to calculate the moment of this thing times its moment arm, the moment of this times its moment arm. find the net resultant, because now we have another distributed load. We have the lift of the wing, the lift of the tail. And depending upon whether this net force acts behind the CG or whether it acts in front of the CG, it's going to tell us which way it's going to pitch in response to the gust. Do you see that? If it's back here, we get that net increase due to the gust, and it's going to pitch nose down to counteract the pitching, the disturbance. If it's in front of the CG, then it's going to do the opposite. In fact, it'll increase the pitch, which will increase that again, which will increase it, and it actually flips the airplane. So two critical things. We need to make sure that we can get equilibrium, but then we need to make sure the net resultant force acts behind the CG, and we can actually calculate that point. That's like the aerodynamic center of the airplane, because we add the wing and the tail and everything else together. So we'll spend a lot of time making sure we can trim our airplane when we build it, and that we get the pitch stability. That is, the disturbance generates a moment, a nose down moment. And the way we talk about this in pitch stability is that we want this thing to happen, is that in response to an alpha increase, we want a negative nose down moment to be generated, because that returns back to equilibrium. So the fundamental concept of pitch stability is that for a positive increase in angle of attack, we want a negative pitching moment, or in terms of coefficients, right, Cm is just m over q bar s c bar. We want a negative pitching moment change due to that. So we'll actually write that as a ratio. We want that to be zero, less than zero. We want it to be negative, or in the limit, we'll write this as the change in the pitching moment with respect to angle of attack needs to be negative. So we'll actually calculate Cm, take the derivative of it, and look at it and see, is it negative or positive? This says if you have a positive alpha change, we want a negative pitching moment change, and that gives us the stability. So we can even check this. We could take our airplane in the wind tunnel and plot. We could put the airplane at different angles of attack, measure the total pitching moment, and see whether this slope is positive or negative. So go ahead and build a wind tunnel model of your airplane. It's a radio control airplane. You just stick the thing in the wind tunnel. You do an alpha sweep, and you plot. So you take your airplane in the wind tunnel, and you get this plot that I'm going to draw. So in the wind tunnel, you do an alpha sweep, and we're going to do this in terms of coefficient, Cm, and you get a plot that looks like this. Here's your trim. Why is that trim? Pitch trim or trim? What's the slope? Is that a positive slope or a negative slope? It's an easy question, right? It's positive. So is this stable or not? Oh, look over there. It should be negative. Tomorrow, what do? You go in the wind tunnel, you get that. You're supposed to fly tomorrow. You're scheduled to fly. What do? You what? Yeah, you're going to have to change your center of gravity or something, right? You don't just go fly because you'll crash for sure. And there's a team a while back that actually did that. They went in the wind tunnel. They got a plot that looked like that. They went into Dr. Miller. You guys want to fly tomorrow? And the guy that was in charge of stability and control said, we're unstable. And the rest of the team said, we got to fly tomorrow because we're supposed to. And guess what? They flew and they crashed because a gust came along and they pitched up and then they stalled and they fell and crashed. So what you want is the opposite of this. We're still okay on time, or yeah, okay. So that's unstable with an E at the end. What you want is to go into the wind tunnel and you see a plot like this. Again, this is trim because the pitching moment there is 0 at that angle of attack. And this has a slope that's negative. And notice both of these pictures I've drawn with a positive angle of attack as the trim. And that's important because typically you need a positive angle of attack to get positive lift to stay in the air. So that's the force balance. Lift has to equal weight. The book makes a big deal about whether this y-intercept is up here or down here, and that tells you whether it's stable or not. And that's true because if you have a positive alpha trim, then your intercept's going to be on one side or the other. Forget that. I want you to just look at the slope. If the slope's positive, you're unstable. If the slope's negative, you're stable. And here we're talking about pitch stability. So hopefully you learn more than this from this class, but if you only remember 2 things, when you go to build your airplane, first off, make sure you can trim it in pitch. And second, make sure that you have pitch stability on the airplane. One other just bit of notation, often, and we'll do this all the time, right? In this class, we write CL subscript alpha, and what we really mean is the slope of the lift curves, right? It's just a shorthand notation of writing the derivative. We do the same thing with pitching moment. We write CM subscript alpha, and that is this derivative that we've been talking about of the slope of that line. Okay, the next thing we'll do is we want to look at various different ways to build an airplane and find out, well, can we make it trimmable and can we make it stable in pitch? And we'll start out with just a wing alone, a wing plus a horizontal tail, a wing plus a canard in front, and various different things. So we'll do that next time. Again, remember your homework is due uploaded to Blackboard, one single PDF file in order, so it's easy to grade, uploaded by the deadline, which is when? Wednesday at 10:20, right? So why did I make it 10:20? Class starts at 10:30. I don't want you guys running around trying to upload your files and being late to class. So this just kind of forces you to be ahead of the game. Okay, see you guys on Zoom on Wednesday. See the Zoomers, some of the Zoomers in here on Wednesday. Let me see if there's any chats. There's some where they're popping up that. Oh, pray there's no wind. Drop out of senior design. Okay. Yeah.